Well, welcome everyone. Thanks for joining us today. Before we get going, I want to introduce CAS, which is the Consortium for the Advancement of Scientific Software. We are an HPC-oriented scientific software stewardship group. We're composed of other stewardship groups, and we're supported by the um, Department of Energy Office of Advanced Scientific Computing Research. We have a few different working groups that work together to put these stewardship efforts out into the world, one of which is the User and Developer Experience Working Group, which puts on these webinars that you're attending right now. The working group is open for you to join. We have these webinars that we put on, and as well as a discussion hour that's on the even months at the same time slot. But our goals are really just to improve user and developer experiences for research software, to create a sort of community and create more knowledge within the community. Our next webinar is going to be on May 5th, and we'll be having our most design-oriented topic. So we'll be talking about designing to reduce cognitive load next time. Leah Kim from Fermilab and Mike Morrison from CurveNote will be our speakers. The slides from today's meeting and prior ones are accessible on Zenodo, and the recordings are going to be put onto the CAS YouTube channel. I'll put these links to Zenodo and CAS and YouTube all in the chat once we've gotten going. And I mentioned that there's a discussion hour on even months. So our next discussion hour is on April 7th, and you're invited to register for that as well. We'll be talking about web pages for HPC software. So who should they target? What issues do you have maintaining them? We'll talk about common usability issues together. It's a really informal setting to get to learn with one another. So with that, I'm going to turn the floor over to our speakers. Olivia Newton is a researcher and instructor at the University of Montana, where she studies teamwork in science and engineering. And our second speaker is Andrew Schmader, a science IT consultant at Lawrence Berkeley National Lab and creator of our lab's AI services portal, which we call Seaborg. He's a member of the American Science Cloud Intelligent Interfaces Group as well. Olivia is going to speak first, and we'll have some time for questions at the end of her talk. And then at the bottom of the hour, Andrew will have his presentation and questions afterwards as well. So thank you, everyone. Please feel free to type questions into the chat or ask them when they're called for at the end. I'm going to stop my sharing, and Olivia, you can get going when you're ready.
Great. So I'm going to share my screen and let me move some things around. Can you all see my screen all right? This should be the title slide that you
Yeah, it
see.
looks great.
Awesome. Okay, let me move this Zoom toolbar because it always gets in the way. All right, so hi folks, thanks so much for being here today, and special thanks to Hannah and the CAS User Developer Experience Working Group for organizing this webinar and for inviting me to talk with you all about some of the research I'm working on with my collaborators at Argonne National Laboratory and the University of Illinois Urbana-Champaign. So as the title of this presentation implies, I'm going to talk to you a bit about teamwork and then AI, and then I'm going to talk about the blend of AI and teamwork in the context of scientific computing. I also want to emphasize the preliminary findings part of this headline here. This is a work in progress that will continue to evolve. So I'm excited to share this first look at some of our findings with you all. Let's move on to my next slide. So before we jump into the science, here's a bit about me for those of you who don't know me. I completed my PhD in modeling and simulation at the University of Central Florida in Orlando, Florida. And then I was a postdoctoral scholar in the Cognitive Sciences Lab at the Institute for Simulation and Training at UCF. In the fall of 2024, I joined the faculty at the University of Montana in Missoula, which is on the far west end of the state. I'm not in Butte. I'm in Missoula. UM is located at the intersection of five major mountain ranges in the Rocky Mountains. So here's a picture of me hiking one of those ranges, the Bitterroot Mountains, which also provide a nice view of the Sapphire Mountains. Needless to say, it was a big change going from Florida to Montana. So, on to the science. First, I'm going to talk about the overarching project that today's research is part of. I'll then move on to provide some detail about our study sample before I talk about those preliminary findings. Okay, so some context for this work. The research I'm presenting today is just one part of a much larger project titled Next Generation Ecosystems for Scientific Computing, Harnessing Community, Software, and AI for Mission-Driven Team Science, which gives you an idea of the broad scope of the work associated with this project. The goal of the project is to assess and transform team-based scientific software that is scientific software developed by at least two collaborators, with an emphasis on building ecosystems to address the needs of next-generation research in scientific computing while advancing emerging AI technologies. I have the good fortune of working with a very lovely group of collaborators, including Lois Kerfman McGinnis and Anshu Dubey at Oregon National Lab, and Denise Ward Hood and Santiago Espina Tavares at the University of Illinois. And of course, that's me as well. So, the Next Generation Ecosystems for Scientific Computing project entails several thrusts of work, two of which I'll highlight now. The first thrust is a workshop series organized to initiate conversations about pressing issues in computational science and engineering, particularly with respect to teamwork, cross-disciplinary research, and emerging AI technologies. These conversations are helping shape the research we're doing in this project. With respect to broader engagement, we're considering activities like birds of a feather submissions to conferences and exploring community venues such as the Trillion Parameter Consortium. I'm going to take this opportunity to shamelessly plug the report from the year one of the workshop series, which you can access with the QR code or the bit.ly link on this slide. So please do check that out. The second thrust here is our team's research, which aims to characterize the key roles and factors that contribute to the success of scientific software development teams. And that's in addition to the communities that support and rely on scientific software. Ultimately, our goal is to contribute to the development and customization of best practices guides and training materials for these teams and communities. As a first step, we focused our efforts on identifying and specifying the challenges and opportunities that exist for team-based scientific software, including cross-disciplinary collaboration and AI for science, which leads us to the research I'm presenting today. So this research utilizes survey and interview methods to elicit perceptions and perspectives on teamwork, software, and AI in scientific computing. Our study population consists of anyone who works in scientific computing as part of a team, so they don't necessarily need to be in the trenches writing code if they're part of a team that's developing, maintaining, or contributing to scientific software in some way. They are welcome to share their perspective. So we first distributed an online survey, which included both closed and open-ended items about these topics. We also asked our survey participants, of which we had 79, if they'd be interested in a follow-up one-on-one interview. And over half of them indicated that they would be interested and provided their contact information. And I highlight that because I think it's really important how passionate this community is about their work, and especially about these topics. There's a lot of opinions and thoughts, and also needs to work more effectively and in a way that's more satisfactory, not just in terms of performance, but enjoyability of the work. Thus far, we've conducted interviews with 14 individuals, and we selected this subset with the goal of maximizing variation in the interview pool to ensure we capture the diverse perspectives that are present in the scientific computing community. At this point, I do want to once more offer the caveat that this research is ongoing. In particular, the qualitative data analysis component is still very much in the early stages, and we still have a lot of data to go through. So with that, let's talk about our survey sample, and then we'll jump into the results. Who completed our survey? Most reported that they were employed at the national labs or in the academy, although we see some distribution in other categories as well. The average tenure in their current role is well over 5 years. On the demographic side, most participants identified as men, and the mean age was in the mid-40s, but we also have some good spread there. When asked about what role they work in, as this plot shows, most participants reported that they worked in a science, software, or faculty role. On the x-axis here, we have the number of folks who reported belonging to that category. Only a couple participants reported that they work in a research software engineering role. They're binned into this software category, which includes folks who identified themselves as software developers, software engineers, and the like. So let's talk about teamwork. We asked our survey participants a number of questions about teamwork. One of the items that stood out when looking at the data was how awareness of best practices for effective teamwork in scientific computing was spread. So participants were asked to indicate their level of awareness on a 5-point scale, which is plotted here on the x-axis. And we see that a lot of folks fall into the moderately aware and somewhat aware group. Another way to look at this is if we split the moderately and very aware folks into a high awareness group, and the somewhat aware all the way down to the not all aware group into a low awareness group. We have a near 50-50 split. And I'd argue that this suggests that there's some room for improvement, as there are some best practices out there, both for the collaboration component and the software component of this work. So how to do team science and how to write high quality software. Related, I haven't broken it out here, but it is worthwhile to mention that in the slightly aware and not all aware category, we did have some folks who identified themselves as holding leadership positions. So just something to think about. In addition to asking about awareness of best practices, we were interested in learning about what members of the scientific computing community felt they and their colleagues would benefit from in terms of training. So responses reflected a desire to learn more about how to better take the point of view of others, how to communicate to folks who don't speak the same disciplinary language, how to handle conflict and maybe some difficult personalities, but also how to be a good leader, and in particular, how to be a good principal investigator working with students and early career and junior folks. Participants did also express interest in training for software quality and reproducibility. And part of the reason why there's more items in the team science category here than the software development category here is just that this question primarily focused on team science competencies. And then folks had the opportunity to identify additional areas of training that they would like. So that surely primed people to think more about team science than software development. We did have some items that we'd say fall somewhere in the middle, where folks want training for students to work in scientific software teams. So they need both of those team science and software development competencies. There's also a desire for more training on agile methods, and systems thinking. So being able to step back and see the whole and the interconnectedness of various components of a system. Lastly, we have folks who also want to better understand how and when they should use AI tools and what appropriate reliance on AI tools looks like, which leads us to some of our AI results. We, of course, had to ask folks how often they were using AI in their scientific computing work. And unsurprisingly, we see that occasional to frequent use is the norm. Participants indicated the frequency of use on a 5-point scale, which is here on this y-axis. It's pretty clear from this plot that most folks fall somewhere in that nebulous sometimes category. Interestingly, when we divide this data by those who identify themselves as working in leadership or not in a leadership role, the always group is made up entirely of folks in the leadership role. So with everyone using AI, or nearly everyone using AI, at least in this sample, we might have some ideas about what the best use for AI is in the context of scientific computing. Unsurprisingly, perhaps there is no consensus, and here's my silly little doodle, not AI generated. Um, when asked about the single best use for AI in scientific computing, some say there's no good use, some say there are specific good uses, others are waiting to see how things unfold before they want to identify any such use. Even when focusing on responses describing a potential best use for AI in scientific computing, we see that there's still no clear consensus. Some responses are very code-centric, including everything from code generation to code refactoring and conversion. Other potential best uses focus more on texts, so generating them, editing them, and summarizing them. Lastly, we have some best uses for AI that represent a more expansive category or set of tasks. Like some folks suggest that AI is good for individual learning. Others suggest that we should only be using AI for well-defined problems, that is, problems that we already have a solution for and there's a constrained solution space. And others suggest that AI is best suited for the work that we really don't want to do. And the work you don't want to do, of course, varies from person to person and who you talk to. But for example, one participant notes, what I really need is AI tools to take care of all the stuff that is in scientific collaboration, like annual reporting and compliance training and managing travel and dealing with new policies and 1,000 other things I have to spend my time on that aren't science. So we know folks in scientific computing are using AI to varying degrees in their collaborative work, but are they talking about that AI use in their teams? In particular, are teams discussing AI use policies, whether they should be implemented, what they should cover? In this sample, we see that the majority report that they are not having team discussions about AI use or policies for AI use, which I think reflects a problematic reality. A lot of folks are feeling their way around the dark when it comes to AI, and perhaps worse, they're doing it alone. Another way of framing this in terms of teamwork and team cognition is that there's a need to develop a shared mental model for AI in teams. And in particular, there's some evidence that there's no good task or technology mental model shared across the team with respect to AI, which can contribute to challenges with respect to collaboration processes, how people are working together, and collaboration outcomes, how well those teams are able to perform and how satisfied they are with those collaborations. Among the teams that are discussing and implementing AI policies, um, topics covered include things like keeping data and information safe and secure. Here, folks are really interested in ensuring that data stays out of the wrong hands. So that includes malicious actors, but also that the data or information isn't leaked in some accidental way. Um, Next, we have ethical and legal use of AI. So folks are talking about how to use AI in a way that does not violate the law or some other requirements for maybe ethical or responsible conduct of research. Um, there's also some discussion about, just disclosing when you're using AI, how and when AI was used. And next, we have research integrity, so ensuring, that whatever was produced by AI is meeting some level of quality, ensuring that there's integrity in the research. in terms of accuracy, completeness, so on and so forth. Next, we have standards for publishing, given that AI was used in some aspect of work. So, how do you handle authorship in the case that content was generated by AI? How do you communicate information about that AI use? Again, transparently, but also in a way that is honest. And then at the far end, there are some policies which are strictly prohibitive. For example, forbidding the contribution of code that no one having written it, no one understands it, it immediately causes a bus factor of 0. So some teams are talking about AI use and some aren't, which leads to our next question. Is AI changing how your teams collaborate? And again, there's a lot of variation in responses. This is some of that data that we're still combing through. And so I won't have complete results here to show you, but at a high level, some said yes, some say no, but most are probably somewhere in the middle. They aren't really sure or haven't really thought about it before. Some very directly said, I hadn't thought about that before until you asked me. Um, so some folks, I think are very busy in their work and they don't often have the time to sit and reflect on these things. And also, I think is related to why so many folks were eager to share their views in a deeper sense over interview, right? Is that they don't often have the time or opportunity to get to talk about their teamwork, to get to talk about these higher level concerns that affect how they work together and in teams. So I think something here that's important is people are being prompted to reflect on these topics. But although we are still coding the data, we are beginning to see some themes, including the perception of AI as a tool that enables teams to meet their goals, contributing to the team's ability to rapidly develop software, get results, and publish them. On the more negative side, we see that AI may introduce or magnify some undesirable collaboration dynamics. In this example here, we see some issue with the ability of team members to recognize each other's expertise. So one participant writes, "My greatest frustration is a few teammates shortcutting the critical thinking process, getting code from an AI bot, and then relying on it and arguing against my own decade of expertise in manually debugging and coding." So I wanted to highlight this quote because the unique value of teamwork, generally and in this context, is of course the integration of varied expertise to solve complex problems that span disciplines and domains. So a failure to recognize each other's expertise means that the team will be less effective in leveraging each other's expertise. And that has potential to impair team performance, but it also contributes to diminished team satisfaction and viability, the degree to which you enjoy working in that team, and the likelihood that you will continue working in that team if given the opportunity to do so again. So we are, of course, still working through this data, and we really look forward to being able to share these results once they're finalized. Reiterating what I said on the previous slide, we hope these findings don't simply inform us of the state of the world in scientific computing, but also encourage dialogue about these issues in a deep and meaningful way within scientific software teams, your teams, the scientific community more broadly, so that we can improve our work and our happiness in the work we do, right? So that's to be continued. Some takeaways, maybe some participants and interviewees report having few opportunities to learn, not just software engineering, but specifically to learn how to be a better collaborator, how to engage in collaborative problem solving. And they express wanting these opportunities. So there's a need to develop, tailor, and provide opportunities for teamwork training that can really strengthen collaboration. That's, of course, a necessary condition, but it's not sufficient. We also need to make a concerted effort to increase awareness of existing and emerging resources, including best practices. Um, that folks are putting together. I think we all know that one of the challenges in scientific work and scientific software in particular is dealing with information overload and cognitive overload. So perhaps this would be an opportunity to integrate some of these resources into existing tools or alongside these tools, almost like documentation. We see in this study and in other research that there really aren't good or sufficient standards for AI use, and that those who are creating policies tend to be more on the permissive side, focusing on issues of legality and security. Lastly, AI is perceived as beneficial to team efficiency and team performance outcomes, but may also have some negative consequences for team dynamics and could contribute to undesirable outcomes like team conflict. So, with that, I want to acknowledge that this work was funded by the Department of Energy Office of Science, Distinguished Scientist Fellows Program. And I thank you all so much for being here today, listening to me talk, and for sharing your own thoughts and perspectives on this research.
Thank you, Olivia. That was great. I'm really looking forward to the rest of your results. I think it's really interesting how the team context and dynamics can influence use of AI tools and vice versa.
Mhm.
Yeah, the interviews are going to be great. We have time for a couple questions if someone wants to raise their hand or put something into the chat. I can be quiet. I have one.
Okay.
What do you make of the leadership being in the always uses group?
Um, I think I'm going to speak from personal experience now in my own institution. Um, Administration, there's a lot of folks who are interested in, I think, seeing the success of AI. And part of the success of AI is widespread adoption. And for folks in leadership position, I think that's part of it. But I think folks in leadership position are also very crunched for time. They have 5 million different tasks to do, including administrative work. So I think anything that can ease the workload or the burden of the number of tasks that need to be completed is a welcome, you know, tool or a welcome addition to their workflow. Um,
There's a couple comments and questions in the chat, and maybe Andrew can get it set up while you maybe respond to one of them.
yeah.
Brad asks, do you have any thoughts on how the use of AI for code generation might be impacting perspectives on the importance of code quality?
I think this is, at least in our data and some of the things I've seen, this is very split. There's very like polarized views on this. Some folks are holding on very tightly to the need for software quality, that maybe it's actually growing the importance of software quality in their perspective. Like, this is the opportunity where we really have to get this right before it gets completely out of control. And then we have some other folks who um, I think part of it is a lack of understanding of the importance of software quality, that they're like, we can it's a trade-off that they're willing to accept, that as long as we are able to get some output, as long as we're able to get a product, um, that we can make do with some diminished quality.
Thank you. I'm going to turn the floor over to Andrew now, and Olivia, feel free to keep answering questions in the chat.
Okay.
Thank
Uh,
you. That was wonderful.
yeah, thank you. Thank you very much. Thank you, Tyler Coles, for your comment. Um, um, and then, so the question from Alfred Tang, has there been any study on the place of politics in teamwork, for example, or software and scientists identified as Republicans less well received? How about the place of religion in software and science teamwork? There is definitely some work on politics and religion and teamwork. It's not my area of study, so I can't speak too deeply about it, but I might be able to send you a few papers on that topic. And then there's one more comment. I bet a bunch of those leadership folks are also one-time programmers who haven't had time to write code in a while, but now can do it in their spare time. Yeah, I think that's a fair assessment.
Ready when you are, Anna.
Yeah, thank you, Andrew. Andrew comes from Lawrence Berkeley National Lab and is going to be talking about, I'm going to abstract to some AI tooling. Um, I've been really looking forward to this talk as well. So I'll be quiet and let you have the floor. Thank you.
All right, thanks. Okay, thank you, Olivia, for all those interviews and everything. I'm going to be taking a look at some of the technical side of this question of can AI do scientific coding? And as Hannah mentioned, I've been setting up and running some of the AI sort of AI gateway portal for Berkeley Lab for a couple of years now. So I've had a chance to test a lot of these models and talk to a lot of people about kind of what their experience is. So yeah, there's probably a curve of folks on various sides of the equation. I think a lot of us can agree that the tools are okay for some things, but have limitations. So here's like one of the claims that is coming in through the media is like from Sam Altman saying, you know, GPT-5 is like having a team of PhD experts. And then these kind of sensationalist comments like, oh, we're having a closed door briefing and we expect PhD level super agents are coming, and everyone is spooked and scared. I'll note that this was actually from a year ago, January 2025. So we haven't seen the super agents yet. Another claim that I've seen, and that's interesting to me, is this claim that LLM inference is actually getting effectively 10x cheaper each year. And that isn't true at like the API costs of using large language models has actually stayed about the same. But this particular analysis that was done basically says, well, if you instead look at like the cheapest model that achieves a sort of minimum level of a sort of fixed level of intelligence, that model is getting smaller and smaller and therefore cheaper year over year. So these are a couple of things that I wanted to kind of investigate further through basically running my own benchmarks rather than just relying on what's been published. So there's a few reasons to strongly consider that running your own benchmarks is actually a good idea. One of them is detecting misconfigurations in your own systems, in your own code. So there can be all kinds of things, like maybe you just have the wrong model name. You might have like incorrect generation parameters, and these can affect how the model performs. There's also inconsistent publication. So vendors don't consistently publish benchmarks for every benchmark. They kind of pick and choose the ones that they want to announce. In particular, there's one called SciCode, which is what I'm going to be talking about today. There's also a need to test like non-default configurations. For example, some models can be quantized to different levels, and unless you benchmark it, you will have no idea of what the effect of that quantization could be. And furthermore, there's many different ways of quantizing models. So you're not going to find like published benchmarks on every single different quantization of a particular model. It's just something that you're going to need to do by yourself. And again, there's other parameter tweaks that can be done, as well as a major effect, which is modifying the reasoning budget that models use in order to kind of search their internal memory space before they answer. This can have a very profound effect on the quality of the result. And finally, the main goal is to measure what we care about, i.e. what scientists at Berkeley Lab and elsewhere care about in terms of using these models for scientific applications, and especially managing the costs, which is a major issue that I'm seeing everywhere. Here's my screen going. Yeah. All right. Okay. Try this again. So SciCode is a benchmark that's published online. You can find it at this GitHub link. It's a scientist curated with multiple disciplines going across 5 different domains. It has a quantitative evaluation of the correctness of the code. So it includes like data sets that are then given to the code that's written to verify that they're producing the numerically correct answer. It can also be run in a mode that's called with background, where it gives basically equations written out like in LaTeX syntax, which are the equations that need to be implemented. And it's still a very hard model. So the current state-of-the-art models are very far away from benchmark saturation. And this is a kind of a breakdown of the different domains that it covers. So here's an example of a problem. So each problem is broken down into a main problem and then a series of sub problems. So basically these are like dependent functions. So in order for the main problem to execute correctly, all of the sub problems also have to be implemented correctly. So you can think of this kind of like a little bit more of a realistic simulation of what a typical scientific programming exercise might involve. There's going to be like several sort of sub functions that have to be implemented correctly, and then those are going to kind of roll up the results into like a larger function. So obviously, to get that larger function correct, all of this dependent code is going to have to be also implemented correctly. So in addition, when this test is running, the model is not given access to internet or external tools. I mean, you could try that if you wanted to evaluate how it does in those conditions as well. In terms of the conditions that I've measured, it's always been just the base model with no access to external tools. So this is kind of the high-level results of me testing this, all of the different models under around like 60 different test conditions over the past like 6 to 9 months. And what I've plotted here on the vertical axis is the total cost of running the entire benchmark, which generates which involves processing between like 1 to 2 million tokens. And then the horizontal axis is the percent correct in the main problem. So in order to, as I mentioned before, in order to get the main problem correct, it has to get all the sub problems right. So, and there's usually around 3 of them. So, so for example, currently, like the best performing model here is Gemini 3.1 Pro with high reasoning effort. And it's around like 26% correct on the main problem. If you were to look at the sub-problem correctness, it's around 65% correct, best case scenario. And then this dashed line is the like the Pareto optimal frontier for cost versus quality, which currently runs like right through the Gemini models. And actually, even over multiple generations, Gemini has consistently been at this like frontier position. So I've noticed kind of a number of interesting things about this. Well, first of all, you might notice like the distribution like of percent correctness, it's basically kind of linear. Whereas the distribution of cost is more of a non-linear distribution. Like there are some that are just very expensive and there are some that are incredibly cheap. So some of the observations that are kind of unexpected, one of them is that reasoning does not always help. So in several cases, I've encountered models that have reasoning in them, but they tend to kind of overthink. And in this case, in some cases, it can either drive up the cost substantially without producing any higher percent correctness. And in some cases, actually, I've had models that fail to complete the benchmark because they actually get stuck like in reasoning loops, and they'll just run forever and never return like an answer. Like an example of one of those actually is like a recent example, for example, is a GPT 5.3 codex with like the extra high reasoning effort is unable to complete some of the problems on Scicode bench. And then, in fact, some models even perform worse when you enable high reasoning effort, which is a little bit surprising. And another thing as well is that I've noticed recently is that like you might think like Opus is going to be like consistently so much better than Sonnet because Sonnet's a smaller model, Opus is a bigger, expensive one. But actually, they kind of track much more closely than you would think. So going to a larger model does not necessarily convey like a step change in capability on this benchmark necessarily. It can improve things slightly, but you might actually get kind of about the same result. Now, that said, it's possible bigger models might introduce other capabilities that are useful, but in this narrow measurement of just scientific programming, they don't necessarily operate that much better than their smaller counterparts. In terms of the frontier, like what are the best models? In my observations, Gemini has been consistently like not only the best, but also the most cost efficient. And I think they do price it somewhat aggressively in the market because they are sort of like in a number 3 position after like Anthropic and OpenAI in terms of popularity. It could also reflect like Google's sort of preferences in terms of how they train their model. Perhaps they spend more effort on math and science than some of the other vendors, which might prioritize other things like tool use orchestration, for example. Anthropic, I've actually seen very inconsistent performance, especially from Opus. So like, for example, in version 4.6, it actually scores worse than 4.5, for example. And then also in a few iterations of Opus, engaging high reasoning effort either degraded or didn't improve performance at all. It just drove up the cost. OpenAI, usually they're pretty good, but they're usually not on the frontier from what I've seen so far. Another kind of surprising insight is that I measured also many of the so-called open weight models, and they're actually not price competitive when you purchase them at a per token rate from like a US provider such as Vertex AI, Google Vertex AI. They actually end up costing as much or more than other commercial models, and their performance is generally significantly worse. So sometimes people kind of like are tempted to move towards these for cost saving reasons, but I just don't see a benefit to doing that. If I go back to here, you can see actually like GLM 47 is kind of right here in the middle, which is comparable to say Sonnet 4.6, but when you actually purchase inference for this model, from Vertex AI, the cost difference is extremely small. So I'm not really sure. And it actually Sonnet, you can see here, Sonnet 4.6 did better without high reasoning. So you'll get better performance and cheaper inference from regular Sonnet 4.6. So, and then even better if you just switch over to Gemini 3.1 Pro. So yeah, so kind of circling back on those claims. So here I've tried to look at the different models and see what is their rate of improvement, because I think, right now we can agree that, only 25% correctness on this benchmark means that they're probably far from PhD level expertise as claimed. However, they are getting better pretty consistently. So here I looked at basically the rate of improvement of different model families. And this only covers sort of around like the last 6 to 9 months. But essentially you can see, here's Gemini Pro going from like version 2.5 to version 3 and then 3.1. It's kind of a consistent upward trend. Gemini Flash made kind of a big jump up recently. Opus also kind of had a big step upwards, but then it actually regressed slightly. And then Sonnet has been kind of improving nicely. On average, these models are improving something like 700 basis points per year. So on current trends, if it continues at a sort of linear pace, then this benchmark would saturate at 100% within like around 10 years. So then I kind of switched to look at the 10x cheaper claim. So I had to kind of go back and get some benchmarks on older models. So basically this says, okay, if we fix the level of percent correctness at approximately a certain constant, and then look at like over time, what is the cheapest model that can achieve that percent correctness, then we do actually see these kind of like order of magnitude drops. So, GPT-4.1 had a 7% correctness on this test, and nowadays you can get, the same performance for a model that's 10 times cheaper. Similarly, maybe even more dramatically with like the difference between Gemini 2.5 Pro and then Gemini 3 Flash, like it's a huge gap. So in general, yes, we are kind of seeing big steps down at a sort of fixed level of cost. That said, like, the cost of the frontier intelligence has just remained kind of about the same. So if you want to keep pushing the frontier and using the best model that's available, it's not going to get any cheaper. And generally that is what people want. So I guess the 10x claim is not necessarily useful on a day-to-day basis for a scientist that's actually using these tools today. So yeah, some conclusions. One, PhD level expertise. Well, my observations, flagship LLM can be around 65% correct in code generation for small functions. But when you kind of roll that up into a larger package, the probability of the whole thing being correct is still pretty low. So far from expert. If we equate 100% correctness on this benchmark to AGI, then we can expect that is around 9 to 10 years away. Claim of 10x cheaper per year, that seems to be possibly true. I'm not sure about the long-term trends. We'll see. But there's also like some issues, like there is kind of a practical floor. Like there doesn't seem to be a market for, you know, the hyperscalers to provide extremely cheap access to tiny models. They prefer to provide access to like bigger models, and the old models just get discontinued. They don't get cheaper. And then small models, they're not really viable for like cloud inference, but maybe you'll see them on edge devices or something else. So that's that. Excuse me. And if there's just a little bit more time, then I will show a quick demo of just something I've been playing around with. So, so this is just like some ideas on where things are going with like agentic code development. So this is like a sort of a definition of a multi-agent system written out in YAML. And basically it involves kind of like a multiple steps. So first there's like an interview process where the model will ask you about kind of what you're trying to code. And then it gathers requirements, then hands off to an orchestrator, which then delegates to a worker, and then they kind of engage in a loop until the requirements have been satisfied. And then you can also augment that with external tools. So you can give like your worker access to this tool called Context 7 so that it can look up API documentation. And then you could give it another tool that, for example, writes the code to a file system or even tests it. So basically, as these systems get better at this type of coding, then they can operate sort of for longer in these sort of autonomous workflows. And so here I'm going to kind of ask it for what I want to say. I want to kind of make a PET-C simulation, shallow wave equation in 2D. So it's going to ask me some questions like, which language, different discretization method, boundary conditions, etc. So just kind of give like concise answer to that. And then I'm using this to-do list as the way of notating like the requirements. So you can see over here what it's going to have to do. So it's handing off to the orchestrator and then hands off to the worker, which is going to actually go and attempt to write the code. And I'm using actually Gemini Pro with a high reasoning effort for this demonstration. So yeah, I think this is kind of an interesting, just new direction in the scientific workflow where potentially we can have sort of multiple steps of an agent that can do research or gather requirements, do research, write code, test it, potentially do other steps like searching for data sets, retrieving, moving the data sets, setting up orchestrations. So we're really rapidly approaching a sort of inflection point where things can be reliable enough that they can start to run some of these more extended workflows in this domain. And So it's very exciting. Anyway, happy to just have a couple minutes left. Happy to take any questions.
Yeah, thank you, Andrew. That was great. I do see some questions in the chat. Tyler has one as well. And I also, please correct me if I'm wrong, but I also want to acknowledge that what we're looking at now is not available for other people's use, but it was developed through the American Science Cloud project. Um, just to credit that effort. And maybe Tyler, do you want to go ahead with your question?
Oh, sure. And thanks for doing this benchmarking. I find it really interesting. And apologies if I missed the answer to this question, but when you are evaluating each of these against the benchmark, is this basically like a one-shot score, or are you running this multiple times? Do you feel like there's any value in running it multiple times, or do you get like a pretty stable result?
Yeah, it's a one-shot test condition. So it's it generates the code, and then the benchmark framework, takes the code, which is in Python, by the way. It's generally like NumPy. It's like NumPy. A lot of it's mostly NumPy with like no libraries, so it has like only the NumPy API. So it generates the code, and then it runs the code with the data set to validate that it produces the correct calculation. Now, I don't think it was validating like efficiency, for example. So, but yeah, so it's looking at the correctness. But yeah, if it gets it wrong, it's like, you got it wrong, we're going to move on to the next question. But yeah, you could theoretically connect it to like an agent that tries to revise and get it right. But that would also affect, like, that might improve the results. It might not, but it would also increase the cost of running it too. So we would kind of be able to see that.
Sorry, I guess my question is more like, if you're evaluating, say, Gemini 3.1, do you just do that one time, or do you like do it, 3 times across 3 different weeks and see if the score varies over time?
Oh yeah, some of them I have repeated the benchmark just because I thought it seemed a little suspicious, and so far they've always come back with the same result. But yeah, I mean, that is possible. Like, you never know exactly. Sometimes people claim, "Oh, I feel like Gemini is dumber today," or something like that. I don't know. It is possible. Like, you don't really know. There is a black box, right? So you don't know exactly how they're routing your request in which model and how that one's configured and stuff like that. So, but yeah, I haven't extensively like remeasured them. I would say just occasionally I have.
Gotcha. Thank you.
We are at the top of the hour. Andrew, I don't know your schedule, but there are more questions for you in the chat.
Yeah.
And I do want to thank everyone for coming.
I'll just, if anyone has to go, it's fine. I'll just try to answer. Let's see. Can they answer questions about math and science, or just communicate? Yeah. So yes, these models actually, so they can generate like LaTeX equation syntax pretty well. So if you ask, like, and they can read it as well. So you can read in. Let me see if I can actually find an example so I can show you. Yeah, the correctness score comes from the SciCode benchmark. So when you run the benchmarking tool, it runs it through all like 75 problems and then tells you like which the percent correctness on the main problem and then percent correct on the sub problems, which are generally, they're correlated numbers. So I didn't report on the sub problem. Is there any other, is there documentation? There is a GitHub repo for SciCode. I think I put it here. I can send these slides later if you want me to. So there's a GitHub repo for this with all the code if you want to try it yourself. And Also on the Seaboard website, I have a benchmark code here with the results, which I keep up to date. So it has like the percent correct and like when I measured it last. So yeah, happy to take any other questions offline as well. Thanks.
Thank you very much. Thanks, everyone. This recording will go on the CAS YouTube channel. It'll get linked on our website, and we'll be able to post any shared slides on Zenodo and link them from the CAS website as well. I hope to see you in April for our discussion hour about software project web pages, and in May for learning about designing to reduce cognitive load and support decision making. So thanks again to Andrew Schrader and Olivia Newton, our speakers this month. I hope you all have a wonderful day.